over chapter 12, section 1. So chapter 12, section 1 talks all about earthquakes. So now that we've talked about plate tectonics and we've talked about these lithospheric plates on Earth's surface moving around, now we're going to essentially talk about what is the result of that, of those plates moving around on Earth's surface. So first of all, technically, what is an earthquake? An earthquake is movement of Earth's crust resulting from the release of built-up potential energy between two stuck lithospheric plates. You guys got to imagine that these tectonic plates that are doing all the things that we talked about in the last chapter, sliding past each other, sliding under each other. We're not talking about smooth surfaces here. We're talking about rough surfaces. And you can see it in the picture here on the screen with the one with the two red arrows on it. You can see that that surface isn't smooth. And the same thing is true of lithospheric plates. They're not smooth, so when they move past each other, it's going to be so in a not smooth fashion. During an earthquake, strong shaking makes the ground move up and down and back and forth. There's actually very specific ways that it happens, and I'll talk about that later on. To date, I believe the largest earthquake ever on record was actually in Alaska in 1964. So they have the little screen there on there. The area within that patch on there slipped seaward up to 66 feet. That's quite drastic when you think about it. All right, so earthquakes and plate boundaries. So most earthquakes occur near plate boundaries, occur in the spots where you have two lithospheric plates meeting each other. When you look at all the places on Earth that are the earthquake hotspots, they're almost always near these plate boundaries. You look at Japan, tons of earthquakes happen in Japan, and you can really see why. Look in the picture there. Look at how close Japan is to essentially where three plates meet each other. You have the Eurasian, the Philippine, and the Pacific plate essentially all coming together right there. So this is a earthquake hotspot because plate boundaries tend to be zones of seismic activity. This is just a little kind of picture showing you, if we were to show like where all the earthquake hotspots are on Earth, look at them, and then what do you notice? It essentially lines up with our plate boundaries. Not all of them, you will notice not all of them, but really most of them. And the location of these is actually what has also helped us find the location of our plate boundaries, because some of them obviously are hard to see. So it's kind of a schematic, but here's an actual picture. So this is marking the red dots on there are going to be really deep earthquakes. The purple ones are ones that aren't as deep. I'm sorry, I got that backwards. The red ones are not as deep. The purple ones are more deep. So you can see once again, look at all of those locations and what do you notice? Almost all of them are right along plate boundaries. And what we learned about in the last chapter, it really only kind of makes sense that that's what happens. So earthquake waves, remember they're called seismic waves. So seismic waves produced by earthquakes, we have a few different types of them. The first type that come are called the foreshocks, obviously fore meaning before. So small bursts of shaking, they may precede a large earthquake. They can happen a few days in advance. They can happen only a few seconds in advance, but usually you're going to get some sort of a shaking ahead of time. You're going to have the very distinct seismic waves that we'll talk about later on, but then obviously at the end you get aftershocks. Aftershocks are small tremors that follow an earthquake. They'll sometimes last for an hour, or sometimes they can even last for days afterwards. So when you look at the parts of an earthquake, this picture here, this real simple picture kind of walks you through the parts of the earthquake. So a couple of terms that you should remember is, the first one here is the focus. You can see where it's pointing on the screen there. The point below the surface where the rock breaks is the focus of the earthquake. It's essentially where the earthquake starts at. It's the starting spot for the earthquake is the focus. We don't talk about that though, right? You don't hear that on the news, the focus of the earthquake. What you hear on the news is you hear the next term, the epicenter, right? That's the one you hear. And the reason why we hear epicenter on the news is because that is the point on Earth's surface above the focus. It's where we live. It's what we see. So you'll hear people say, well, the epicenter of the earthquake was in Tokyo. Well, that's just a spot above the ground of where it happened. And we pay most attention to it in the news because it's usually where we see the most damage. So if you look at the focus and you go straight above that to the epicenter, usually that's where you're going to see the most damage. All right, so earthquakes are technically a form of what we call strike-slip motion. A great analogy for strike-slip motion is you've ever pulled on a door before that's kind of stuck a little bit. Happens a lot in the summertime when it gets really humid. You got to open that door, it's stuck, you got to pull a little bit. That's how earthquakes happen. So those two tectonic plates want to move past each other, but they're kind of sticking a little bit, just like that door. Eventually, they're going to slip. That motion, that strike-slip motion, is actually what creates the earthquake. And in the picture here, they're showing you, well, the door opens with a bang. Well, on Earth, when we talk about earthquakes, then it's going to happen essentially in the same manner. All right, so friction, this is all happening because of friction. So remember, friction is a force, or it's a force that's a resistance to slip that occurs when two objects rub against each other. So really, these earthquakes are happening because they're a product of friction between two tectonic plates. Keep in mind that our lithospheric tectonic plates have many sections. So you're not just going to get movement in one spot, you're going to get movement in one spot and it's going to move other things in different locations. Your book uses the analogy of a line of grocery carts. So just like if you go to push a grocery cart in the front of that line, when you push it, you may notice all the rest of them move. The same thing happens with tectonic plates. So although a plate might move as a single unit, like you pushing that single grocery cart, when it interacts with the other ones, it can cause sort of a chain reaction moving with the other ones. So one tectonic plate can essentially move a lot of tectonic plates. So these plate boundaries that we've been talking about can be thousands of miles across. Don't think of them on a small scale. So think about how big our tectonic plates are. They can be thousands of miles across. This picture here, for example, is showing us the very famous San Andreas Fault in California. The reason why California has so many earthquakes. And that's a cool picture there, really showing you really the plate boundary. So some of these we can actually see. So you can see right along there that plate boundary. You can see also in the picture there, they have in red the regions where the plates are locked together, and then in the blue where they're kind of creeping past each other a little bit. So if those things are kind of locked to each other and you get this one spot that's trying to move, remember that whole thing we just talked about with the grocery carts. You're going to get movement along that whole plate if you're going to get movement in one spot because they affect each other. So when do earthquakes happen? As we've been talking about, they happen because of that release of built up potential energy that's happening between those two tectonic plates. Really all earthquakes are, it's just a stress reliever for these tectonic plates that want to move around. So once an earthquake occurs, potential energy is going to essentially build up again and you're going to have the same thing happen again. Your textbook talks a little bit about a famous earthquake that happened in the United States in 1895. It was one of the biggest earthquakes that we've ever had. And if you can see the picture here, it's kind of a weird spot. It happened in Missouri. It's along the New Madrid Fault. So not a normal place for earthquakes to occur. It's just kind of an example showing us that, yeah, it can happen in other places. But yeah, there was actually an earthquake there. All right, so these seismic waves produced by earthquakes, we can pick them up using seismographs. So they are a record of those earthquakes, so they measure them. Now, when those earthquakes travel through Earth, when they travel through the Earth, the seismic waves, we are going to have different types of waves. We just talked about the foreshocks and the aftershocks, but we also have what are called body waves. So these are the seismic waves that travel inside Earth. There's two different types of them. There's P waves and there's S waves. P waves are primary waves. They arrive first. They're the first ones to show up. The reason why they show up first is they travel through everything. So P waves travel through solids, liquids, and gases, show up first. S waves arrive second. They do not travel through liquids. They travel slower. They're called S waves because they are secondary waves. So here is a picture just kind of showing you the spot on the left-hand side of Earth here. This would be where an earthquake occurred at. So keep in mind when those seismic waves are produced, they're going to travel everywhere through Earth. We have seismic waves, or excuse me, seismic stations everywhere on Earth, so they pick up shaking anywhere. So just like if you were to shake a bowl of Jell-O in one spot, it's going to go throughout that whole thing, and we pick up the shake on the other side. And what they found out is there were spots that we didn't see the seismic waves traveling through. And that's really essentially kind of also how we deduced what the inner core and outer core were like, the fact that the outer core is liquid and the inner core is solid. So after an earthquake occurs, the first waves, like we just said, are going to be the P waves. So this is kind of like a fake drawing of what a seismograph reading would look like. But there's the P waves. They're showing up first. You're going to start bouncing around a little bit. Then we have our S waves, or those secondary waves, show up. And then finally, the very last thing you can see in the picture there, the last one to show up is going to be the surface waves. And as you can tell, if you can look at this picture here, the surface waves looks like they are really jumping around compared to the rest of them. And that is the case. Surface waves, I'm going to show you another picture here. Here's another one of a seismograph reading. So we have P waves starting, S waves, and then finally the surface waves. If you've ever shook out a blanket before, like if you've been at a picnic or something, that's really what surface waves do to the ground. They take the ground and just move that ground violently up and down. And obviously you can see, if you're looking at damage from an earthquake, that's literally where the most damage is going to come from, are those surface waves. All right, so we have all of these seismic stations on Earth picking up seismic waves. So then what we try to do is, or scientists try to do, is they try to figure out then, all right, where was the epicenter then at? Where was the focus at where this earthquake originated at? So what they have to do is they have to take information from all of these different seismic stations, and they analyze all the data, and they can use that to figure out where the epicenter occurred at. It's a little bit more complex than just saying at this particular epicenter, it's going to be the most violent shaking that we have. And your book uses this analogy. They talk about if you have two cars racing each other, let's say they're on a quarter-mile racetrack, the track that's short, the track that is so short that fast and slow cars are often just fractions of a second apart. So you see like on the top part. The one on the bottom, though, when you start to look at, we're talking about the Indy 500, so we're doing many more laps, you're doing many more races, the cars might be minutes apart. So essentially what that's just telling you is saying if you're near a epicenter of an earthquake, the seismic waves are going to be really close to each other. If you're farther away, they're going to be farther apart. So I'll just say that again. The closer you are to an earthquake, the closer the seismic waves are going to be to each other. The farther away from an earthquake you are, the farther apart those waves are going to be. So it's the time difference between those waves that we use to try to figure out where the epicenter of the earthquake is at. So these seismic waves radiate out from the focus of the earthquake. 3 seismic stations, that's all we actually technically need, are used, and they take the data from those 3 and they can figure out then where the epicenter of the earthquake is at. So like I just said, the larger the difference in arrival time of those P waves and S waves, the farther it is from that epicenter. Your book talks about an interesting story in where in Africa, they had seismic stations going off all at once, and they tried to start analyzing the data, and really what they came to find out was it was not actually an earthquake. There was a football game, soccer to us, going on at the same time, and then when people were chanting and cheering and moving up and down, they were literally setting off the seismic stations. And I would imagine where we live, when the mines blast, they're going to be registered on a seismic station as well. So how do we measure earthquakes? So this is the one we're most familiar with. So when you hear about earthquakes on the news, most often used as the Richter scale. So Richter scale ranks earthquakes according to their magnitude. So you can see it goes from, we have anything less than 2 up to 9 or higher. The smaller the number, the smaller the earthquake. So the smaller the number, the smaller the earthquake, the less damage. As you work your way up here, you can start to see 7, 8, 9. You're starting to get into territory of serious damage over very large areas. So that is the Richter scale. Here's just another kind of picture showing you, just kind of walking you through here, showing you, maybe with an earthquake of 2 on the Richter scale, you're going to see hanging objects sway a little bit. 5 to 6, maybe you're going to start to see some house damage. Now when you're starting to get into 6, you're going to really start to see house damage after that. Another scale is called the modified Mercalli scale. So this one they use by interviewing people. So after the earthquake happens, they'll actually walk around and then say, well, what did you feel at your house? Did you see stuff move in your house? Did things fall off your shelf? And they actually use a Roman numeral system from that. So they have 1 all the way up to a 10. That's our Roman numerals down there on the bottom. So then based on what the people say, they will assign a value to those areas. And then obviously where they're going to have the most activity happening, then it's going to be assigned a higher value number. There's a little bit of a problem, this one. If you've ever had anything happen before in school, and like, let's say something happens at lunch, someone gets in a fight and you're like, the first person says, oh, so-and-so just push that person. Well, by the time it gets to the fourth person around, it's a completely different story and you know, obviously much worse than it was in the beginning. So human beings have a tendency to over-exaggerate things. So there is probably a little bit more of a problem with this. Now, one thing though with the Richter scale that we didn't talk about is it measures damage. So you can't always look at damage, because what if you have an earthquake that happens in the middle of Alaska and there's like no one living there? Is it still a bad earthquake? Of course it's still a bad earthquake. You just don't have high rises and other buildings above it that became damaged. So often they'll kind of take all of these things into account to try to figure out where the epicenter was at. Here's just one sheet kind of just showing you comparing the Mercalli and the Richter scale with each other. Obviously just similar. The larger the number, the more catastrophic the earthquake's going to be. And here's just some pictures wrapping up for you, showing you some earthquake damage. I think we often think about buildings. It's not always buildings. They do damage to roads, as you can see there, do damage to bridges. California used to have double-decker highways, which I believe they have now since not done, since they had a really bad earthquake 30 or so years ago. If you live in areas where they have earthquakes, life is a little different. You know, it's weird for us here in Minnesota to think about some of the things that they do, but you want to think about, you know, building buildings that can withstand shaking. So putting things in the basement, putting things in the roof when you're talking about really tall buildings so that they can have the ability to move a little bit. When you talk about the pipes in the building, not having the pipes be made out of metal, having the pipes made out of plastic. So if they move, you're not breaking a gas line, because that can be a big damage in earthquakes, is having gas lines be open. And then obviously that's an extreme fire hazard. All right, so lots of information on earthquakes. So earthquakes, just essentially those tectonic plates moving, you're going to have damage up on Earth's surface.